Okay, so last time we talked about the subspaces, and today we'll be discussing two very important subspaces. So first one is the column space, and the next one is the null space. Column space and these two subspaces, they are all associated to a matrix. First, let me introduce a so-called a column space. I have a matrix A, which is an n by n matrix. So since this is an n by n matrix, so I may consider this matrix consists of how many n column vectors. This is a collection of m column vectors, and each of these columns, they are the member of m-dimensional Euclidean space. This is a matrix, and the column space which will be denoted by C of A of matrix A is a subspace of Rn. Is it? No, so subspace of Rm. Sorry, Rm defined by so this is the definition. So this is a definition. So basically, just take all these columns and consider a subspace, consider a collection of all linear combinations that can be generated by these columns. This is the column space. And as I told you, the span of any set of matrices, any set of vectors, it is going to be automatically a subspace. And since each of these vectors, they are the member of Rm, right? So this is automatically the subspace of Rm. So this is a column space. Okay. Now, why do we even care about the column space? Because, well, obviously we were interested in solving the systems of linear equation. Ax equals, well, this is my system of linear equations. This guy has a solution when, if and only if, B can be written as a linear combinations of these columns, right? So in other words, this equation, this system has a solution if and only if B is a member of the column space of A. I know I repeated this so many times, but let me just repeat just one more time. One last time. This x1 xn is, well, this is just linear combination of v1 to vn. Therefore, having a solution is nothing but writing this guy as a linear combinations of the columns of matrix A. So this is that. Okay, all right. Now I realize that I am the only person speaking in this classroom, so I'm kind of getting bored. So I'm going to give you a short quiz, pop-up quiz for this time only. Well, I know this is nothing to do with your final letter grade, but well, let's try to do this. I have a matrix A, and suppose that the column space of this matrix happens to be entire Euclidean space Rm. Then Ax equals to B has a unique solution for all possible choice of B. Is it true or not? What do you think? True or false? This is not true. Why? If I drop this word, then this statement should be true. But why? Because well, since this guy is the entire space Rm, therefore, for every choice of B, this guy must be the member of column space. Therefore, you can find the solution. But however, here I am claiming the solution is unique. Therefore, this statement, the entire statement must be false, right? I will give you an example of this. 1, 0, 0. X, Y, Z, and W. So how many different solutions can you find from this? Well, this B1, X is B1, Y is B2, Z is B3, and W equals to 0. That is a solution of this equation, right? But however, X equals to 0, Y is B2, Z is B3, and W is B3. Sorry, W is B1. That is also going to be a solution, right? So, well, in this case, just consider span of each of these columns. They are all standard unit vectors of R3. So therefore, span of all these columns should automatically regenerate the entire space R3 itself. But however, solution is not unique. Therefore, the statement is false. Okay. All right. The next quiz is what about this? This time, my right-hand side vector is the 0 vector. It always has a solution. Is it true or false? This is true, right? Right? So in other words, 0 vector is always a member of every possible subspace. So therefore, so more explicitly, so if you plug in the X equals to 0, then this equation is automatically satisfied. So it always has a solution. But sometimes there can be some non-trivial solution. We'll return to this issue later. But however, the statement itself is always true. If m is greater than n, n is greater than n. So that means my matrix A is not wide matrix, but this is narrow matrix, right? So narrow matrix. So having a narrow matrix means this system of equation, the number of the equation of this guy is greater than the number of unknowns, right? So if you have a system of linear equation that has whose number of unknowns is less than the number of equations, then most likely you may not be able to find the solution. So, well, in this sense, this statement may be true. No, but if you're so lucky, so I mean, if your choice of B happens to be in the member of the column space, then you can find the solution. Almost always you may not be able to find the solution, but if you're so lucky, so that if your choice of B happens to be in CA, then you can find the solution. So this is also not true, okay? Okay. All right, so this is about the column space. And the another important subspace is the null space. Well, again, my matrix M is an M by N matrix. What is the null space? Null space is usually denoted by N of A. The null space of matrix A is a subspace of Rn defined as just like this. This is a null space. So roughly speaking, so the null space of matrix A is collection of all solutions of this system of this equation, this linear equation. I am asking you, you should be able to convince yourself that N of A is indeed a subspace. Why? In order to be a subspace, then, well, not every subset can be a subspace. In order to be a subspace, then the set must be closed under vector addition and also closed under scalar multiplication. Is it closed under vector addition? Yeah, yes, right? Because if V1 and V2 are the solutions of AV equals to 0, then A of V1 plus V2 also must be the solution of the equation. And if V is the solution of the system of equations, then any scalar multiple of the vector is again the solution of the same system of linear equations. Right? Okay. Okay. So this is a subspace. So A V1 plus if V and V1, V2, a member of NA, then A V1 plus V2. This is again by linearity 0. Therefore, V1 plus V2 is the member of the null space, and alpha of V1 is also the member of null space. Okay, so this is a subspace. Not a big deal. Easy, right? Okay. Agreed? Okay. Now, okay. Why do we care about the column space and null space? Well, because we want to find this. We want to find the solution of system of linear equations. To understand the column space and null space will help you find every possible solution of system of equations, system of linear equations. We are not interested in finding a single solution of equation, but we are interested in finding every possible solution of the system of equations, if there is any. Okay. Suppose that you have a system. You have a system of linear equations that has m equations and n unknowns. Suppose you have this looking system of linear equations. If m is greater than n, in that case, number of equations is greater than the number of unknowns. In this case, most likely you may not be able to find the solution. Okay. And in this case, we say over-determined system. You have too many restrictions compared to the number of degree of freedom. So this is over-determined system. However, if m is less than n, in this case, number one equations is less than number of unknowns. We say this is an underdetermined system. In this case, since degree of freedom, which is number of unknowns, n, is greater than number of equations, number of restrictions, therefore, in this case, solution exists, but the solution is not unique. Well, in this case, number of solutions is infinitely many. And in this chapter, especially on this section, we are typically interested in finding all possible solutions, especially your system is underdetermined. Just find a single solution. Yeah. If solution is not unique, then number of solution is always infinite. Okay. So precisely speaking, the solution set cannot be discrete. So, which is already, as you can see, maybe you will understand maybe by the end of today's lecture, but the solution set usually looks like a null space, the entire null space translated parallelly. So this is how your system says, set of all solutions look like. It's always infinite. Yeah, thank you. Very good point. So I want to find every possible solution of the system, underdetermined system. How? Okay. How do you find all solutions? I'm going to give you two very important observations for a underdetermined system. Suppose A is an m by n matrix. And we consider a system of linear equations Ax equals to B. Now, again, suppose that we happen to find a solution is a solution of the system of equations. In this case, then for any, just choose any random vector from null space of A, then xp, then the xp plus xn is a solution too. Why? Why is that? Because a x p plus xn, well, is axp plus axn, but because of this assumption, xp was a solution, therefore this is b, and axn, since we have chosen xn from the null space, so a times xn must be 0. Okay, so therefore xp plus xn is also a solution. Okay, very easy observation. But however, the converse of the statement is also true. Sorry. This is any solution. Suppose that I have a solution of this equation. Then every solution of ax is b can be written as xp plus xn. Xn in NA. The proof is also easy. Suppose X is any A solution of the system of linear equations. Then AX minus XP is AX minus AXP. But here we have assumed that X is a solution of this guy. Therefore, this one must be. And we have assumed that XP is another solution of the same system. So again, this is B. So B minus B, which is 0. This implies X minus XP is a member of null space. So therefore, X can be written as XP plus some element from the null space. So this is the proof. So just by looking at these two observations, now we can conclude that in order to find every solution of AX equals to B, we have to find any solution. And once we find any solution of this equation, then we need to understand the structure or the shape or the geometry of the null space. If we can understand that, then set of all solution is just merely nothing but the entire null space translated by this much. Okay. So this is the set of all solutions of AX equals to B. So therefore, to find all solutions of the system. First, find any. Oh, by the way, this guy, XP, is usually called a particular solution. So first find any particular solution. And then next, we find a subspace NA. Then by doing so, you can find every single solution of AX equals to B. But there is a question. So if I say you find a particular solution, that is very easy. So just, well, maybe by trial and error, if you find a single vector, then that can be your XP. XP is usually some vector, right? But what do I mean by find a subspace? I mean, how do you describe any given subspace? This is very interesting question because, well, usually, well, you cannot list every single element of the subspace because, well, this guy contains infinitely many vectors. So there should be a very clever and or an easy way to describe any given subspace of Euclidean space. So I will try to describe. So from now on, I will try to tell you how to describe the subspace, the null space of any given matrix A. Okay. In order to be able to describe the null space, this is the key idea that you should understand. The key idea. What is this? Applying. Applying. Do you remember the elementary law operations? And applying the elementary law operations does not change the solution set. Solution set, I mean by collection of every solution of the system. Doesn't change the solution set of AX is B. Right? So whenever a system of linear equation AX equals B given, then by applying the elementary law operations, we try to change this matrix A into more reasonable and computational friendly form. If you can do that, then maybe we can find a solution. This idea or this technique was actually something that we did in the previous chapter, right? Suppose that my matrix A was a square matrix. Then how did you find the solution? You applied a bunch of elementary law operations so that you transformed A into the upper triangular matrix. And doing it by back substitution, then you found the solution. Same trick can be applied to this equation, but this time around, there is one difference. This time, A may not be a square matrix. A can be any rectangular matrix. So we will need to develop an idea or algorithm which is also applicable to non-square matrices. But almost the same idea. The idea is, instead of trying to transform this guy into the upper triangular matrix, we will transform this guy into something more like the upper triangular shape. So this is what we call by a echelon matrix or echelon form. I say this is an analogy of the, well, this is the rectangular matrix version of the upper triangular matrix. suppose that I have this matrix 2, 6, 9, 7, -1, -3, and 3 and 4. Oh, I forgot to bring my book, but I forgot to bring my textbook. But I really like our textbook. The Professor Strang, he tries to spell out all the theories and the principles and propositions regarding the linear algebra, but he tries to spell out all these theories not in abstract manner, but by giving you a very concrete example like this. So try to follow the example and you will understand the theory. You will understand the theory. So that was his way of writing his textbook. And I really like it. So this is his idea. So this is his text. So this is the matrix that he figured out. And we apply the upper triangles. We apply the elementary law operations towards this matrix. How? So when you're doing when I was trying introducing the fourth elimination, I tried to get rid of these two entries, right? Say, well, I'm going to do exactly the same thing for this matrix. By applying the elementary law operations, I want to eliminate these two numbers. How? By multiplying the first law by -2 and add it to the second, and then I can get rid of this. By same trick, I multiply this guy by +1 and add it to the third, and I can get rid of this number. Okay. So then the first law, it just carries over, but the second 0, 0, 0, 3 and 3, yeah, and 0, 0, 6, 6, yes. Okay. Okay. I happen to get rid of these two numbers too. But anyway, I cannot stop at this point because I also want to get rid. I also want to eliminate this number by applying the elementary law operations one more time. So how? By multiplying the second law by -2 and add it to the third, then I can eliminate this number. By the way, if needed, if required, then you may have to permutate the order of the laws. But well, that does change too much. So in this case, so I do not want to consider the law permutation. So I can try to apply the elementary law operations on and on until when? Until you encounter an entire law filled with zeros. So this is where you have to stop. Okay. And this matrix, I want to call this guy as a echelon form of matrix A. Generally speaking, so what is a echelon matrix? Echelon matrix is a rectangular matrix version of the upper triangular matrix. Sorry. Sorry about this cartoonish picture. I hope you understand. This is the echelon matrix. This is what I called a echelon matrix, or in echelon form, the stair-shaped collection of entries. And as you see here, the entries with dot, these guys, these numbers, and because of the construction of the echelon matrix, these entries with dot, they are guaranteed to be non-zero numbers, right? And every entry below the diagonal, sorry, I'm abusing notation. There is no notion of diagonal here. But once you obtain the echelon matrix, then all these numbers below here, they must be all automatically zero, right? And above this diagonal, then there can be some non-zero numbers. And these numbers on the dot, they are all non-zero numbers. And this is the echelon matrix. And these numbers, the numbers with the entries with dot, these numbers are called these are all non-zero numbers. And they are called pivot, the pivot of the matrix. So once you obtain this shape, once you obtain this shape by applying the elementary law operations towards the original matrix A, then we say the matrix A, it has been transformed to the echelon matrix. Yes. Yeah, sure. You can also have the, but in that case, there should be the bunch of zeros, like then all zero. Should be like this. But you're right. Good point. You can also define a echelon matrix for the narrow matrix. Good. Okay. All right. Now let us find the echelon form of the matrix A. Oh yeah, this is the, so therefore, sorry, I did it. So this is the echelon form of the original matrix A. Now, so what is good? Why do you even care about the echelon matrix? Let me find a null space of the matrix A. Well, to find a null space of A is mathematically, that is nothing but find all solutions of this system of equations. So if you can find every single solution of this, then you find a null space, okay? But finding a solution of this equation is the same as this, right? Because applying the elementary law operations doesn't change the set of solutions. So instead of working on this system of equations, let me work on this system of equation, which is mathematically the same as the previous one. Okay. Then this was my echelon form of A. This is U, V, W, Y, and everything 0, 0, 0. Okay. Then I want to translate this matrix equation to the system of equations like this. U 3V 3W plus 2 times Y 0 and 3 times W 3 times Y is 0. So, aha. So therefore, this is the idea. In order to describe the null space of A, I can try to write in this way. U, V, W, Y. So null space is collection of all such vectors satisfying these two equations. Okay. It looks like I didn't do anything. Well, this is the very satisfying answer. This is the very satisfying description of the null space of A. I say this is not very satisfying because, well, at least for me, this is not mathematical statement. This is some sort of psychological statement. So can you find any geometric intuition out of this? I don't know. At least I cannot find any geometric intuition because, well, each of these equations or each of these restrictions, they can be considered as a three-dimensional hyperplane embedded in four-dimensional Euclidean space, right? So, and since U, V, W, Y, they must satisfy these two restrictions at the same time. So therefore, the geometric object described by these two equations is sort of kind of a intersection of two three-dimensional subspaces in R4, right? This is very confusing. Well, I'm not saying this is the wrong answer. This is very right and rigid answer. But however, this is not this. So I cannot find any geometric picture out of this. But this is a well, this is the one description. And I'm going to show you the another description of the null space. To have the another description of the null space, I want to describe, I want to introduce you a so-called reduced low echelon form of any matrix. Reduced low echelon form. So what is a reduced low echelon form? In order to get the reduced low echelon form, we will need to begin from the echelon matrix. Well, say this is my low echelon matrix. And I want to apply another set of elementary row operations. And in this case, these numbers, these pivot numbers, pivot entries, they are guaranteed to be non-zero numbers. And dividing any row by some non-zero number is also allowed in elementary row operations. So let me try to divide each of these rows by entries in this pivot. Okay, then divide by entries on pivot. Then, oops. then I am not that interested in. I am not interested in these entries. So, then I want to emphasize that these pivot entries now they are going to be all ones, right? Okay. All right. Good. Then now what? Now can you see these entries above the pivot? In this case, this is an entry above the pivot, and these two entries they are also above the pivot. These entries they are all entries above the pivot, and what I'm going to do next is I want to eliminate all these entries above the pivot. Suppose that this number is say 7. In order to get rid of this number, I multiply the entire second row by -7 and add it to the first, then I can get rid of this number. By doing so, these numbers can be 0. So now I can make these guys to be 0 and these guys to be 0 and these guys to be all 0. So all these entries above the pivot, they are now 0. This matrix which I'm going to call it R, is a reduced low echelon matrix or reduced low echelon form of A, or sometimes RREF of A. This is the reduced low echelon matrix. Can you find any similarities any similarities of this algorithm with some other algorithm that I introduced before? Do you remember? Well, while we try to find the inverse matrix, sorry, I changed my mind. So this echelon form or this echelon matrix was analogy of the upper triangular matrix. Reduced low echelon matrix is an analogy of the identity matrix. We have seen this kind of algorithm before. So when you try the Gauss-Jordan method, when we try to find the inverse matrix, then by applying the elementary law operations, we try to convert the left-hand side of the equation matrix equals to the identity matrix, right? When you try to convert the reference side to the identity matrix, then we actually did precisely the same thing, right? Because we transformed the left-hand side to the upper triangular matrix. Then we also try to get rid of every single entries above the pivot, above the diagonal, just by this method. So I can say this is the rectangular matrix version of the identity matrix. Okay. All right. Okay. This is a reduced low echelon form. This reduced low echelon matrix. Let me try to find the reduced low echelon matrix of matrix A. If what was my U? Yeah, this was my U. If this is my echelon form of A, then reduced low echelon matrix is going to be here. This is already 1, so I don't need to multiply anything for the first row. And this is 3, so dividing everything by 3. So I will have this right? Now I want to multiply -3 to the second row and add it to the first. Then, right? And I'm done. So this is the reduced low matrix, the reduced low echelon matrix of original matrix A. Okay. All right. Now we have the reduced low echelon form of A. Now we can, I can give you the another description of the null space of A. Finding a null space was equivalent to say find all solutions of this system of equations. But this is again equivalent to ux is 0. But this is again equivalent to rx equals to 0, right? So this time around, I'll be working on this system of equations. U, V, W, Y. So I have this, and you know, these two numbers, they are called the pivots, right? These are pivots, and here you need to multiply this 3x4 matrix to 4x1 column vector, and these unknown is now being multiplied to this pivot when you multiply the first row by this column, and this W is also going to be multiplied to this pivot entry, right? So from now on, the unknowns that is being multiplied to these pivot entries, in this case, U and W, they are going to be called pivot variables. From now on, we are going to call these two guys as pivot variables, and all the other variables other than the pivot, and these variables, we are going to call them free variables. So these are free variables. Okay, such a weird naming, isn't it? But you're going to understand why they named it like this. So now we have the pivot variables and free variables. Okay, just forget about these namings for now, and let me try to translate this matrix equations into this: U plus 3V invisible W and minus Y is 0, and W plus Y is 0. So I ended up with these two equations, right? Now what? I have these two equations, and I want to solve these two equations for pivot variables. How? Solving these equations for pivot is going to be very easy because of the construction of the reduced low echelon matrix. These entries, they are guaranteed to be 1, right? So all you have to do is just send these two guys to the other side, right? This is how you solve this equation for the pivot variables. And by doing so, I can write every single pivot variables in terms of the free variables, just like this. Okay. Okay. These are all basic elementary algebra. But now, there is a benefit in doing so. Okay. So I can say all these u, v, w, y's satisfying these two equations, they are the member of, then it is going to be the member of the null space. So if this vector is a member of the null space, then if and only if u, v, w, y, well, now I want to replace each of these pivot variables by these two expressions. Then minus 3v plus wy and v minus y and y is just y. Y just carries over. Now I want to rephrase this vector like this: negative 3, 1, 0, 0 plus y times 1, 0 minus 1, 1. Right? Now this is the conclusion. Now I know why these v and y, they are called the free variables. Because you are free to plug in any number you like in the place of v and y, right? Then no matter which number you plug in for these two free variables, the resulting vector is automatically going to be the member of the null space. So by doing so, I may conclude like this: every element in the null space can be written as linear combinations of these two columns, right? So in other words, this is the conclusion. Null space turns out to be the span of these two vectors. Now let me compare. So this is another description of the same vector, same subspace. This NA, this null space of A, was previously described as set of all vectors satisfying these two conditions, or the same subspace is this time around is a span of these two vectors. Which one do you prefer? Well, again, this is a very psychological statement, but I prefer this description more than the previous one. Why? Because by doing so, even though I cannot imagine 4-dimensional vectors, but I feel like I can feel like I have two vectors, and just consider two-dimensional space embedded in R4 contains these two vectors, and these two vectors is sort of generating this entire two-dimensional space. That is the geometric description of n null space of A. Right? So this is very nice and tight description of the null space. Well, which one is better? This one or that one? I told you, I feel like I told you that this description is better than the other one. But well, there's no such thing in mathematics. They are all mathematically important and equivalent, right? So you should be able to do so in both ways. Okay. Just one more thing to add. The number of free variables is, well, I'm really sorry that I haven't given you the definition of the dimension. But I just keep saying the dimension. Sorry about this. but number of free variables is the same as number of dimensions of NA. Can you see why? Because I have two free variables, these two V and Y, and the number of vectors that generate the entire NA is the same as the number of free variables, right? So therefore, I can say the dimension of the null space is the same as the number of free variables, right? Okay. This is also very good, very important description, observation. All right. So now we are done about the null space. Now I want to solve the system of linear equations, AX is B. You have to remember that solution of the system of linear equations exist. Solution exists if and only if B is a member of CA. Now, this is a question. Just for any randomly chosen B, how do you know in the first place that B can be written as linear combinations of columns of A? How do you know that? This is a highly non-trivial question. I'm going to show you an example of this. Where was my A? Oh, yeah, this is. Suppose that this is my vector. Suppose that this is my matrix A, and let me say I have column vector B, which is like say maybe 1, 2, and 3. Now, how do you know the column vector 1, 2, 3 can be written as linear combinations of these 4 column vectors? Can you see this? No, at least for me, I can do that. So in order to answer this question, then I will need to convince myself that B must be actually the member of the column space from the beginning. If that is not true, then there is no point to finding a solution of this system, right? So, now, is there any condition that I can, so how do I know any randomly chosen vector B is a member of the column space? There is a very nice way of identifying this. 2, 6, 9, 7, 1, minus 3, 3, 4. U, V, W, Y. I want to find out condition such that this column vector is a member of this column space. In order to find such a condition, then I will need to change this matrix into the echelon matrix. So by applying the elementary law operations, this is 1, 3, 3, 2, 0, 0, 0, 3. This carries over. And for the right-hand side, B1 is B1, but B2 minus 2 times B1, since, well, I have to multiply -2 to the first and add it to the second. So this is why I have -2 B1 here. And by same trick, B3 plus B1. Now I have to do one more row operation. this to get rid of this, I need to multiply -2 here and add it to the last. So 1, 3, 3, 2, 0, 0, 3, 3. And B1, B2 minus 2 times B1, and B3 -2B2 plus 5B1. Am I right? Oh, yeah, this is the sum. Yeah, I'm right. So now my matrix A has been turned to the echelon matrix. Oh, and there is also very important observation. The last row of this echelon matrix is the zero vector, right? Now, in order to have a solution, I also need this last entry of the right-hand side equals to 0, right? So solution of AX is B exists if in order to have a solution, then B3 minus 2 times B2 plus 5B1 must be 0, right? This last entry must be 0. Also, on the other hand, if B3 minus 2 times B2 plus 5B1 equals to 0, then this last entry equals to 0. Oh, well, I'm not that interested in these two numbers. So I'll just put 2 stars on the top, and I have zeros on the bottom. So if this guy equals to 0, then by changing everything into the reduced low echelon matrix, was it 1, 1? Yeah. U, V, W, Y. And so these two numbers must also change. But well, again, I'm not interested, so I'll just say they are 2 stars. Then U is -3 times V plus Y plus the star, and W is -Y plus this star, right? So, what is this? If this guy equals to 0, then I can find the solution for every random choice of V and Y. Then you can actually determine these 2 pivot variables U and W. So that means you can find a solution. Okay. So what kind of lesson can I learn out of this? The solution of this system exists if and only if this gun equals to 0, right? So this is two-sided implication. But solution of this guy exists if and only if B is A in the column space of A. So this means the column space of A can be described as B1, B2, B3, such that B3 minus 2B2, 5B1 equals to 0. This is my another description of the column space. And sorry, 3, 9, 3. Oh, no, sorry. So let us compare this description and that description. Which one do you think is easier? In this case, this is again a psychological statement. I prefer this description more than this. Why? Because, well, these two things they are both mathematically correct descriptions, but if I persist maintaining this description, then I can never be able to tell if any given vector B is a member of the space. But this time around, if I have this description of the column space, then, well, all I need to do is just check if this condition is met or not. And if this condition, if this equality is true, then I can automatically see that the vector is actually indeed a member of the column space. Okay. Sorry, I'll just copy and paste. All right, so this is our final exercise of today's lecture. Let me try to find every single solution of this system. Well, first thing that you will need to check is if the right-hand side is indeed a member of the column space or not. Is it? Well, in order to check that, then this is my B1, this is B2 and B3. And just by looking at this condition, this is 1, B2 is 5, so B3 is 5. Oh, so this condition is actually satisfied for this B1, B2, and B3. So I know, so I can find the solution, right? Now, I want to change the right-hand, A into the reduced row echelon matrix. U, B, W, Y of, say, then this is -2, 1, and 0. So U is -3 times B plus Y minus 2, and W is -Y plus 1. Okay. So therefore, the solution UBWY is minus 3v plus y minus 2, and v is just v, and w is minus y plus 1, and y is just y, and this is minus 2, 0, 1, 0, plus this. Okay. So it turns out that this is the particular solution xp, and this is my xn. Any random element from the null space. So I could say, so the solution of this equation, solution of this system, consists of the sum of those two vectors, xp and xn, right? Okay, so this is for today, and thank you for your patience, and see you next time.